What's the point of making groups? Is the assignment in group or individual?
The first assignment is individual. The other two assignments you can do in a pair if you want. Okay, just a reminder that it's a bit loud. Just a reminder the first assignment has been released, and I think you've got about 2 more weeks to do that. So make sure you get started on it. And if you have any trouble with TensorFlow or with the assignment in general, please come along to one of the lab sessions to get some advice. So today we're going to talk about convolutional networks. So when would we want to use a convolutional network? Well, there's this particular task, and this is really where deep neural networks really came to prominence around 2010 or so, is that it started to outperform other methods on this task, and the task is image classification. So you have a set of images, and when you're given an image, you're trying to determine what kind of object is in that image. Is it a bird? Is it a plane? No, it's Superman. Is it a dog? Is it a cat? Or whatever. You have some number of categories, and you have to categorize the image into one of these categories. Now, this is image classification. There's also image segmentation. Sometimes there's multiple objects in the same image, and you want to actually identify all of them, or as many as you can, and where in the image they are. We'll talk more about that either later or next week. But this is a sort of classic task, is image classification. So we put the image in one end, and at the other end, the outputs try to tell us what object is in that image. Now we could try to do this perhaps with a fully connected neural network, the kind of networks we talked about last week, the fully connected network. So we've got a whole bunch of inputs. We could treat each pixel as a different input. we could choose a certain number of hidden nodes. We could have a 2-layer network. We could have a certain number of hidden nodes. We would connect all of the pixels to all of the hidden nodes, and then we could connect the hidden nodes to the outputs. And if a 2-layer network doesn't do the job, we could try to do a 3-layer network or a 4-layer network or whatever. But people started to realize, and I guess this was really people like Leon Schwarm and Jan LeCun in the 1980s started to think, well, maybe we can come up with a network architecture that shares the weights across the image and makes use of what we know about the structure of images. So, for example, let's say we're looking to see whether there's a bird in the image. Well, what is a bird? Well, a bird would have, if it is an image of a bird, you would expect it to have a beak and maybe an eye and some feathers. You know, there's often components that make up an image. And so, well, first of all, if it's a multi-layer neural network, you kind of have this idea that early layers in the network might detect some of these smaller components, you know, like a feather or something like that, and then they sort of get combined in the later layers. But the other thing to notice is that if you have network weights which are trained to try to recognize a feather in one part of an image, then the same weights would very likely also work to recognize a feather in another part of the image. You know, and some objects are like specifically located in certain places. You expect the sky to be in the upper part of the image and not the lower part. But a lot of these things could actually be in different parts of the image. Feathers could occur in a lot of different parts of the image. So the idea here is we have a network which actually kind of shares weights around in different parts of the image in a kind of shift invariant way. And we'll go through this in more detail in a minute. But that's the idea. And so you build up a network where you have like a convolutional layer, and then you have some downsampling layers. So when you do the convolutional layer, you end up with neurons that are arranged in a spatial pattern, similar to the original image, perhaps the same kind of size as the original image, but then you may have like downsampling where you go into a smaller structure. So some of these things come from traditional image processing. I don't know if you've played around with XV or GIMP or something like that, but you can shrink an image if you don't have if an image is taking up too much memory and you want it to be smaller. There are ways to shrink an image to half of its original size, and so on. So it's the same kind of thing that's going on here. So typically we have convolutional layers and pooling layers, and then at the end then we have some fully connected layers, and then a bunch of outputs, and one output for each possible category. And this is partly inspired by the brain anatomy that we talked about in the first week. So this is the famous work of Hubel and Wiesel. So you've got cells in the primary visual cortex which respond to lines at certain angles. And then you've got cells in the secondary visual cortex which respond to slightly more sophisticated features, maybe corners or circles or different shapes like this. And then, you go further on, higher into the brain, into the cortex, and somehow the brain figures out what the object is. Right now, and we'll see in a moment. Later on, I'll show you. Well, maybe I'll just skip to the end just to show you, but that we can actually, once these convolutional networks are trained, we can actually kind of do some visualization using the same kind of techniques we discussed last week. We could what's going on here is you ask, this is kind of like, the first one, this first layer thing is actually a Hinton diagram, but then these things about the second and third layer, the way they're built up is you say, well, okay, you pick a neuron in the second layer and you ask yourself, to which image would this network, to which input image would activate this particular neuron most strongly. And so you can actually create an image that way. It doesn't tell you the full information, but it tells you quite a bit of information. And this is actually the kind of thing that we observe. So in the first layer, we have these linear features that are actually very similar to what Hubel and Wiesel described. They're sometimes, in image processing, these are sometimes called Gabor filters. So you can see how they identify certain lines at certain angles. And then the second and third layer build up more sophisticated features. And I think I mentioned this is trained specifically on images of motor vehicles. So you kind of get wheels and fenders and that sort of thing. Okay. So there's some neuroanatomical inspiration for this. So we look at this in slightly more detail. So as I said, there's 4 different components that go into this. So there are the convolution layers which extract these shift invariant features either from the input or from the previous layer. We have subsampling or pooling layers which combine activations from multiple units into one unit. So you get a smaller layer effectively. And then you have some fully connected layers which are the same as what we discussed before with the traditional neural networks where every node in one layer is connected to every node in the next layer. And finally you have the output layer where you have one output for each class. And here's just some examples of some of these data sets that these networks would be trained on. So this is the MNIST data set that you're looking at with the assignment. So this is like handwritten digits in black and white. But other data sets so if we want to move on to something slightly more sophisticated, we could look at actual images of actual objects. So a very commonly used data set is called the CIFAR data set. So this is the same kind of size as the MNIST in terms of the number of classes and the number of images. I think there's either 50 or 60,000 images, and there's 10 different classes. So plane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So there's only 10 classes here, and it includes some animals and some vehicles. And these images are fairly low resolution, and they're similar in resolution to the MNIST. I think these MNIST are 28 by 28. These CIFAR examples are, I think, 32 by 32, or maybe I got that the other way around, but they're approximately that size, 28 by 28 or 32 by 32. So this data set was specifically designed to be a fairly small scale data set that people could use to just run some initial experiments to try out a few ideas before they move on to a larger data set. Now, then there's a larger data set that's called ImageNet. And ImageNet, instead of 10 classes, it has 1,000 classes, and it has 1,000 images in each class. So there's 1 million images altogether and 1,000 different classes. So that's the kind of serious industrial-sized data set, the ImageNet. And there was a competition that used to be run every year. I think it was run every year up until 2016 to see who could get the best accuracy on that data set. And from 2010 onwards, well, 2012, there was a particular, there was a network called AlexNet, which did particularly well in that competition. And then every winner since then has been some kind of convolutional neural network. So we'll talk in the second, we'll talk later today some details about how that competition has evolved and what kind of networks people have used over the years since 2012. Okay, so here's another picture of the same architecture, but makes the thing a little bit more explicit. So you can have multiple steps of convolution followed by pooling before you reach the fully connected layers. So this here describes one of the early architectures in this class. It's called Linnet. I think Linnet is. I think it's a play on Jan LeCun, and it dates back to around about 2002. So this is, computers were a fair bit slower then, and we didn't have the GPUs that we have today. So it was built to be manageable by the computers of the time, but the basic elements are already there. Okay, we talked about this last week. This is what happens at the output layer. So remember, we're going to train this thing by backpropagation. So we need to have an error signal at the output layer. And the way we typically do that, because we have to distinguish between these, if we think about MNIST or CIFAR, we're trying to distinguish between 10 different classes. So we have 10 different outputs. And the way this works is that you assume that the probability of if the output for a particular class J, you have output Zj, and then you assume that the probability of that class is e to the power of Zj. So if there's a fixed distance, so if you were to add a constant to all of the outputs, then it wouldn't change the probabilities. This is all kind of normalized so that the sum of them is equal to 1. And so what it means is that if the distance between one output and another output, determines the ratio of the two probabilities. So if this output is 1 higher than that output, then this is more likely by a factor of e, which is 2.71828. If the distance between this output and that output is 1/2, then this is more likely by a factor of the square root of e. If it's 2, then it's e squared, and if it's 3, it's e cubed, and so on. And you can figure out these numbers. So e squared is approximately 6, e cubed is approximately 20. So this enables us to take those network outputs and convert them into probabilities, and then we do maximum likelihood based on that probability. So the training is done to maximize the probability that's assigned to the correct class. So the log, if I is the correct class, then the log of the probability of I is Zi minus log of the sum of e to the Zj. And as I was saying before, in practice what this does is that it pushes up, that term Zi has the effect of pushing up the correct class. So no matter what the correct class, no matter what value the correct class currently has, there'll be pressure for the network to increase it. And the other classes will all be pushed down, but the higher one, if you look at all the incorrect outputs, there'll be pressure on them to be pushed down, but the higher ones will be pushed down more strongly. So if there's some class which is actually incorrect, but the network's giving it an output that's equal or higher or similar to the correct output, then this training will push that down. But if there's some incorrect class that already has a very low output, then the network won't do much to change it. Okay, so now we get to this convolution. Now, this comes from convolution in mathematics and physics. So, and I'm mainly putting this up just to make you aware of the different notations and the relationship between them. So, in mathematics, we often use, or physics, we often use the star operator to show the convolution. So, if you have a time, and often we do convolution in time rather than space. So, in mathematics, you see this. You know, you've got two functions, x and w, and if you convolve them, you get some function s, and s of t is the integral of x of a times w of t minus a dA. That's the continuous version, and then we can do a discrete version. So if it's a discrete version, you're doing a sum instead of an integral. But notice the minus sign. So in mathematics, we usually have a minus sign here, and the minus sign is mathematically nice because it makes the operator commutative. X convolved with w would be the same as w convolved with x. But when we're in computer science, when we're doing something computationally, it's a bit annoying to deal with this minus sign. So usually we get rid of it and we just define convolution like this. I mean, it's essentially the same thing, but it's just done this way for computational convenience. Yeah, and so we get this formula, and now I'm going to go through in some detail. This is a very important concept, so I'm going to go through in some detail to try to demonstrate this. Yeah. If I can get this overhead camera to work. So, yes. Yes. So the real definition, the definition for our purposes, the definition is the third line, the one with the 2 dimensions and the plus sign. Yeah.
So usually it means that it's discrete. We're using
discrete, yes. Yeah. Good. Okay, so this is all right. So let me have a look what we have here. Okay, so let's imagine that, oh, that's weird. Not sure what happened to that other camera. I hope this one is the one being captured. Let me just try this one more time. Okay, don't know what happened there. So let's suppose that this is an input of a. Let's suppose this is an input image, right? It's very small here, but this is just a demonstration. So this is an image that's only 7 pixels by 6 pixels. And this is a color image. So it has 3 different what we call channels. So because it's a color image, it's separated into red, green, and blue. Yeah, so you have the red channel, the green channel, and the blue channel. So for each pixel, you have an intensity that's red, green, or blue. And depending on the format, in some formats, this intensity is a number between 0 and 255. But we can scale it so that it's a number between 0 and 1 is probably an easier way to think about it. So every box here gives us a number between 0 and 1, and this is the red channel, this is the green channel, and this is the blue channel. Okay? Now, we're going to input this to a neural network, and we're going to have a convolution filter. So someone was asking about you were asking about the formula. Yeah, so this is the formula we're going to use, is this one here. Okay, so let's see, you have a particular pixel J and K. Yeah, so the row is J and the column is K. And this green, so these numbers V represent the inputs. So VL, this represents the pink values in layer L at a certain location. And so they're the inputs, and then these Ks are the weights, and the weights are represented by these green boxes here, and they're indexed by L, M, and N. And so I want to calculate, I have one neuron in the next, this is the input layer, and then I'm trying to calculate something in the next layer, in the first convolutional layer. So this is the first layer in the neural network. And the way I do it is I have this inner loop that goes through these green squares. So say, okay, the value here is going to depend on this small part of the image, which is only 3 by 3. Okay, so this part of the image here is going to determine the value of that particular node in the next layer. And so what I'm going to do is first I'm going to have a bias, BI. So I calculate this sum. So I start out by having the bias. And then what I do is I step through M and N in this green box. So M and N start at 0, and this I'm going to use a little coin here to show which thing I'm currently calculating. Okay, so I take the pink value is the input, the pink value here, and then I multiply it by a weight, and the weight is determined by this green box. So I take this input multiplied by this weight, and I add that to the sum. And then I increase n, and now I'm taking this input multiplied, this pink input multiplied by this green weight, and I add that to the sum. And then I take this input multiplied by this weight, and I add that to the sum. Okay? Then I move down to the next row, and I repeat the process. Okay, so this input times this weight, this input times this weight, this input times this weight, those all get added to the sum. And then the next row, this input times this weight, this times this times this. Okay? Now, that's only taken in, so I'm building up this sum in order to compute this one node in the next layer. But so far, I've only taken account of the red component of that part of the image. I've got to take account of the other components as well. So I move on to the next layer, so that I move from the red layer to the blue layer, and I repeat the same process. So you can see how I've got this inner sum with m and n, and then I've got this sum over L. So that's a sum in this instance, this is a sum over the red, green, and blue. So I move on to the blue, and I repeat the same process with the blue. This times this, this times this, this times this, this times this. And they're different weights. The weights for the red layer, there are 9 weights. I specify nine weights for the red layer, 9 weights for the green layer, and 9 weights for the blue layer. Right? Sorry, red, green, blue usually. Okay, so the red, and then the green, and then the blue. And the blue, we do the same thing. We step through like this and multiply each input by the corresponding weight. So we have this sum, and how many components are in this sum? In this case, well, there's the bias plus the 9 weights for the red layer, plus the 9 weights for the green layer, plus the 9 weights for the blue layer. So that's 9 threes are 27, plus the bias is 28. So I've got a sum of 28 numbers, and then my sum is finished, and then I apply the transfer function. So this g here is the transfer function, and which in this case, let's think of it as the ReLU, you know, the ReLU. So after I apply the transfer function, now I've computed one node in the next layer. Okay. Yes? How many nodes in each layer? I'll get to that. So we've computed one node. Now after we've computed one node, what we do is we slide this window along and we repeat all of these computations for this part of the image instead of that part. Okay, so we're now computing the next node of that layer, and so we go through the same process. We have the bias, we have the inner loop with m and n, so we go through each row and each column of the green bit, then we move to the other layer and do the same process, and then we move to the next layer and we do the same process. We get our second node. Yeah? So now you tell me how many nodes. So let's get to the question of how many nodes are going to be in the next layer, right? So how many places can I put this? How many places can I, this, by the way, this green thing is sometimes called a filter. This terminology comes from traditional image processing. So how many places can I put the filter? Well, I can put it here, 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 or here, right? 1, 2, 3, 4, 5. So by the time I get to there, I will have calculated 5 nodes in the next layer, right? So this is, in a minute we'll talk about padding and stuff in a minute, but in this example, this thing actually shrinks a bit because of the size of the filter. Okay, there's 7, the original image is 7 wide, but I only get 5 nodes in the next layer because this is 3 by 3. So the width of the next layer is going to be this width plus that width minus 1. Right? 7 plus, no, sorry, this width plus 1 minus that width. So this is 7 plus 1 minus 3 gives me 5. Yeah? And then how many columns am I going to have? 4. There'll be 20. Okay, so by the time I've gone through all of these loops, I get 20 nodes in the next layer. Yeah, because this is 6 plus 1 minus 3. Yeah. So I go through all of this and I've computed these 20 nodes. Now, notice there's an extra there's an index here that I haven't talked about, which is I. So this is like one channel in the next layer, but if I want, I can have multiple channels in the next layer the same way we had multiple channels in the input layer. So I could bring in a completely new set of weights that calculate some other channel. Yeah, so if I want a second channel, it's got its own set of weights that are completely separate from these weights. But I go through exactly the same process to calculate that channel, and you can have as many channels as you want. You know, I could have three sets of weights and 3 channels, or I could have 16 sets of weights and 16 channels in the next layer. You know, it's just a matter of, it doesn't have to be the same numbers in the input layer, it's just whatever my computer will handle. Yeah? How do you decide the weights? By backpropagation. I'll say a bit more about, were you going to ask the same thing? Or no?
It's very similar. Well,
yeah.
How do you determine the size of the filter?
Okay. Yeah, okay, so 2 good questions. Let's take your question first. So the question was, how do you determine the weights? Well, the simple question is you do it by backpropagation, but, sorry. Well, you just, at the very beginning, you initialize them to small random values. The weights in each channel have to be different. Yeah, otherwise they would stay the same. That's right. So, yeah, so it is done by backpropagation, but there's something a little bit subtle in your question because the weights, well, this is sometimes referred to as weight sharing. So the weights here are the same weights here and the same weights here. So the green weights stay the same as this slides along. So when we do the backpropagation, we get a contribution to these green weights here, and then we get another contribution here and another contribution here. So it's like the same weights appearing multiple times in the computation, but they must remain the same. So effectively, this is like you have to every time you place this filter, you get differentials for those weights. You get weight updates for the same weights in every position, and you have to add up all of those weight updates to get you the combined weight update. Yeah. Fortunately, TensorFlow does that for you. It's part of the automatic differentiation. Yeah.
Do we have to go row by row, column by column, and then layer by layer? Does the order matter?
The question was, does the order matter? The order doesn't matter, but this is this is part of TensorFlow, and NumPy is that the Python libraries try to parallelize the computation, and they try to do it in a way that's as efficient as makes the best use of the hardware that you have, right? So the order doesn't matter. The order doesn't matter. So if you've got a big enough GPU to do all of it in parallel, then that's fantastic. If otherwise, it'll try to figure out the best way to break it up. Yeah. So the compiler effectively, there's some implicit compilation going on, and it may change the order of the summation in a way that makes the computation more efficient. Yeah. Yep.
Are there any limitations for G functions?
G. Well, okay, so this is where I don't know about limitation, but there are certain traditional functions. So in the old days, people usually chose a bounded G. So they tried to have a sigmoid function or tan H, but somehow for these deep networks, people have now more commonly started using this ReLU. So the ReLU is actually for negative x it's equal to 0, and for positive x it's equal to x. So sort of when you first see it, that seems like a bizarre choice, but somehow it does actually do a good job. Yeah, there's just a few G functions that people typically use, and for particular types of network, there's often like a standard transfer function. Yeah, people have looked a little bit into some other types of transfer function, but there's certain ones that are more common or traditionally common, yeah. But it's still not very well understood how ReLU really works, or what kind of geometry it really imposes on the space. People have started to look a little bit into that. Yeah. Good. So let's. Oh yes, you have a question? Yeah.
Yeah, the size of the filter. Yeah, how do you work it?
Oh, the size of the filter. The number of filters? No, the size of the filter. Oh, whether it should be 3 by 3 or 5 by 5. Okay, we'll talk a little bit more about that as we go along. Yeah. Okay, so this is just a summary of what the example we were just going through. So if you have an original image that's J by K and there's L channels and the filter is M by N. So in this example, J is 6, K is 7, L is 3, and M and N are 3. And then the size, we talked about this. So if the original image here is J by K and the filter size is M by N, the next convolutional layer will be of size J plus 1 minus M crossed with K plus 1 minus N. So let's have a look at, so this was a toy example. So let's look at a small but still realistic example. Yeah. Okay, so the question was about the channel, right? So there's two separate things here. So the input is kind of, the number of channels in the input is determined by the type of input. So typically if it's a black and white image, there'll just be one channel. If it's a color image, there'll be 3 channels, yeah? Now, but then the number of channels in the hidden layer, we can choose whatever we want. Yeah, it's just like a number that we pick. So in the Lunette, we have 6 channels. But in some cases, we may have 32 or even 96. Like, it's quite surprising in a way how many channels they actually throw at this. So let's look at Lunette as an example. So in this case, with color images, so those CIFAR images are 32 by 32. And let's suppose that we have these filters that are 5 by 5. Right, so M and N are equal to 5 and J and K are equal to 32. Now, the first question is what's going to be the size of the next layer? Well, it's 32. It's 32 plus 1 minus 5 is 28. So there's 28 different positions you can have for that filter before it bangs into the next, the other side of the image. And then here's a little exercise to help us understand this architecture. So let's suppose that there's 6 filters in the next. Let's suppose there's 6 filters in the first convolutional layer. So how many weights would there be per neuron? So if I have an individual neuron, remember the size of the filter is 5 by 5. So 5 by 5 is what? 25. So I've got 25 weights for each input channel, and there are 3 input channels, right? So that's 75, and then I treat the bias as a weight as well, right? So it's 1 plus 5 times 3 is 76. So each neuron in the next layer will have 76 inputs if we include the bias. Yeah. Okay. Is that clear to everyone? Now, how many neurons will there be in the next layer? There are 6 filters, and each filter is how big? Ah, right, sorry. There's 6 layers in the next layer. Right, sorry, the filter is 5 by 5, but how big is going to be the next layer of neurons? Is going to be what by what? (28 by 28). That's right. So the number of neurons in the layer is 28 times 28 times 6. Yeah. There's 6 channels, 6 layers, and each layer is 28 by 28. Now, how many connections are there? 6 is the number of channels. That's right, in the hidden layer.
Does it mean channel? Does it mean that it's different type of input data?
Maybe I shouldn't use the word channel. I think the best would be to just use channel for. Okay, maybe I shouldn't have used that. So maybe we just use channel to talk about the input. And then at the next layer, we talk about layers instead of channels. I think that would be better. So there's 6 layer. No, well, we can't talk about layers. Okay. Sometimes we call it a filter. Sometimes we call it a channel. But both of them are a bit confusing. But each filter. Okay, so each filter. The filter is only 5 by 5. But that filter creates for us an array of neurons that's 28 by 28. Maybe that's a better way to say it, yeah? And there's 6 filters, so each filter gives us 28 times 28 neurons. But they're all in the same layer. Yes, I shouldn't use layer either. So these are all in the first layer. Yeah, so there's 28 times 28 times 6 neurons in that layer. Yes? Why do you have 1? The bias. We treat the bias as a weight. That just gets added. It's not multiplied by anything. How do we get which? 3 colors. The input is has a red, green, and blue component. Good. It's good you're asking these questions because it helps us to clarify this. Yep.
That channel,
Yeah.
it's a different type of input data. We have 3 colors,
Yes.
and it's like 3 type of data.
Yes.
The channel is like type of data, input data.
That's right.
But why there are 6 filters? So is it or in the start? It's by definition?
We can choose the number of filters. So each filter has the same, we use the same equations for each filter, but the weights for one filter are completely separate from the weights from another filter. So one filter might detect lines at this angle and another filter might detect lines at that angle. Yes? Yeah.
How did you get 6 channels from 3 channels?
6 filters, right? So if the input has 3 channels, but at the first layer of the neural network there are 6 filters, and each filter gives us an array of 28 by 28 neurons. Yeah.
So what, maybe we multiply the 6 in the first portion, weight per neuron, here, but
Per neuron. Yeah.
where we did put all 6 filters in this.
Every neuron belongs to one filter.
So we have 6 different filters, right?
Yes.
And each neuron, once you apply the 6 filters separately, at each neuron, you will apply 6 filters.
No. Each neuron belongs to one filter. So there's 28 by 28 neurons in one filter and 28 by 28 neurons in another filter, and there's 6 filters. Yeah.
Out of 4,000 of these neurons are all in the same layer,
They're all in the same layer.
so they ended up bigger than what it was?
Yes, yes, it's bigger than the input. That's right. Yeah. So we'll talk about that. So there's something funny going on here. We talked about autoencoders where you have fewer neurons. Here, you're right. The number of neurons is bigger than the input. So there's some risk of overfitting, but we'll talk about some techniques people use with this to try to avoid overfitting. Yeah. So how many connections are there? Well, this is the connections is the number of neurons times the number of weights per neuron. Okay, so it's 4,704 multiplied by 76. Now, here's a key question. How many independent parameters? So that's the number of connections, but remember there's weight sharing here. So what's the number of actual independent parameters? What's the number of separate weights, separate independent parameters in the network? You know, like, because one weight is repeated multiple times, or, you know, multiple connections. So how many independent parameters are there here? What did you say? 28 times 6? 25 times 6? It's something times 6. Okay, it's actually 76 times 6 is the number of independent weights. Because these 7, if we think about the weights per neuron, for one neuron, all the weights into that neuron are independent. So there's 76 independent parameters for each filter, and there's 6 different filters. So there's actually only 456 parameters, independent parameters in this network. So that figure of 357,504 is, you know, multiple copies of each of these weights. You know, there's several connections which are constrained to have the same value. Yeah. Yep. Look, okay, what's the advantage of having more than one filter? Well, okay, so, sorry, let me just, can I just put your question on hold for a sec? I just wanted to go back to the question about overfitting. So someone was asking about why there's more nodes in this. Well, I guess this is the, okay, so someone was asking about the fact that there's more nodes in the hidden layer than in the input layer, yes? Now, but in a way, if we're really talking about overfitting, what we're really talking about is the number of independent parameters compared to the number of images. You know, so even though there's a huge number of weights here, so far we've only got 456 independent parameters, which isn't a lot, you know, but some of the later networks we'll look at will have more, you know. But when we talk about overfitting, it's really this value that's most important, is the number of independent parameters. Now, someone was asking about different filters. Well, I think the best way to think about it is like this. I mean, I have to tell you, some of these architectures, I think it is a bit excessive, the number of filters people use. You know, 96 filters seems a bit excessive to me. But I can certainly see why you might want to have, you know, 30 filters or so, which is what's shown here. So each of these, so these filters, this is from a similar network, but with slightly different numbers. So these filters are actually 11 by 11 instead of 5 by 5. But we have 30 filters here in the first layer. And you can see that each filter is pulling out a kind of different feature. Who was asking you were asking the question, yeah? Each filter is kind of pulling out a different feature. You know, one filter is saying, this filter is trying to tell you whether there's a line in that direction. And this filter is trying to tell you whether there's some color differential in this direction between bluish and orangish. Yeah? And so on. So this is the kind of information that the filters are giving us. And there is room for at least 30 different filters to give us different information. They're not kind of doubling up. Is that a satisfactory answer? Yeah. Sometimes people use too many, but you know, this seems quite reasonable. Okay. Good. Okay. So we've gone through these numbers. Now this is just so. Let's just look at this whole Linnet architecture again. So this kind of gives a bit of a pictorial display of this. So you've got so this is the first layer in this Linnet architecture. So here are the 6 different filters. So remember, this input image is 32 by 32. The filters, each filter just looks at a sub portion of the image that's 5 by 5. So that gives you activations that are 28 by 28. And there's 6 of them. So far we've looked at this part. Now, now what happens from here to here? Well, what goes from here to here is called subsampling or pooling, and the way it typically works is by what's called max pooling. So the way max pooling works is I've got an array of 28 by 28 neurons, and I want to reduce it to just 14 by 14. So I look at little blocks of 2 by 2 neurons, and I pick out the maximum value in this block of 4. So I say, okay, well these 4 neurons here, the biggest value is 6. So I copy that across. The biggest value here is 8. The biggest value here is 3, and the biggest value there is 4. Now again, it looks a bit strange at first, but remember, this is designed specifically for image processing, and it's designed to work with the ReLU. So the thing about with the ReLU, you can't have a negative. The ReLU never gives a negative answer. It's either 0 or it's positive, if the input is negative, you get 0. If the input is positive, it's equal to the, as if the sum is positive, it's equal to the sum. So the value always gives a positive value, and we're picking the maximum of those positive values. Now, if we had an activation function like tan h, which can take on positive and negative values, then we might want to look at taking the maximum absolute value rather than the actual maximum. But let's just think about this in terms of ReLU. So we're just picking out the maximum value. Now, why does this... All right, so we have a little thing like this. Right, so we have the convolutional layer gets these 28 by 28, and then this max pooling reduces each block of 28 by 28 to just 14 by 14, because I pulled out the maximum value from each group of 4. And then I do another convolution. Now this convolution goes from 14... Okay, these is again 5 by 5, but this reduces the 14 by 14 to 10 by 10, right? And for some reason I decide to have 16 of these. And then I do another max pooling. So this max pooling gets me from 10 by 10 down to 5 by 5. And then all of these nodes are connected. Then I have these two fully connected layers. So I have some nodes here, and all of these nodes are connected to these nodes, and all of these nodes are connected to these nodes, and all of these nodes are connected to each output. So that's the entire architecture of this Linnet convolutional network. Now, okay, so someone was asking how to decide how many filters. Well, I can just give you a couple of... Well, the short answer is you just sort of try a bunch of different things and see what works best. But I can give you a couple of tips about this, or some general principles. So the first thing to notice here is how this... Let's think for a minute about what this subsampling does. The size of these arrays is shrinking as you go to deeper layers, right? We started out with 28 by 28, then we went to 14, and then 10, and then 5. And so the size of these arrays is shrinking, which means that each node here, so a node here only depends on this part of the image, right? It's very local information, but the information becomes gradually more global as we move through the layers in the network. So a node here, right, each node here corresponds to only a 5 by 5 portion of the original image, but each node here corresponds to a 10 by 10. The 5 by 5, but each node here corresponds to a larger portion of the original image, and each node here corresponds to an even larger portion. So you have fewer nodes in the array, but each node is encoding information that corresponds to a larger part of the image. Yeah? And then eventually you get these... So the nodes start out highly localized and then gradually become more and more delocalized. And then when you get to the fully connected layers, they're in some sense totally unlocalized, right? So nodes here somehow compute information about the entire image, not just some portion of it, right? So you get this sort of gradual delocalization. And the other thing to note is it's quite common that the number of filters increases, that it's quite common that as you move through the network, the number of filters well, as you can see, the size of each filter shrinks, but it's common that the number of filters increases, right? So because each node here is corresponding to a larger part of the original image, we need more filters because there's more information that needs to be stored somehow. You know, if 6 filters was enough to capture the information in a small part of the image, it may be that you need 10 filters to capture the information in a larger part of the image. That's just sort of the idea, yeah? And then the final tip is that this issue about the independent parameters. So we just calculated that the number of independent parameters here was 462 or whatever it was. Now, you can go through the same process to calculate the number of independent parameters at each layer in the network. And, well, a rule of thumb that I like to follow is that the number of independent parameters should be comparable at each layer. You know, you shouldn't, if you've got like 1 million independent parameters at one layer and only 500 at another layer, you're probably doing something wrong. You know, so you have to have a sort of balance between, you have to have a kind of balance in the different layers, and the way this balance is achieved is related to what I was saying before, that you could see the number of nodes in each layer is kind of kept in balance as well, because there are fewer nodes in each filter, but there are more filters. Yeah, so that's usually the case. I don't know. Does that make sense? Does anyone have any questions about this? Yes.
When you're doing pooling subsections, you're doing function.
The question was about pooling. So with this max pooling, well, no, usually the pooling doesn't involve any transfer function. There's this, you don't, there are some networks where you don't do max pooling at all. If you use something called stride, that's what I'll talk about next, yeah. Did you have a question? Yeah. Yep.
The second image becomes 5 by 5 by 3.
Right.
So say one of the channels red, green, blue, like 4. So that output's going to be 2-dimensional, right?
Yes.
So you're going to have like 3 blocks, like a red block, a green block, and a blue block, of where they originally came from each filter, right?
Each node in the next layer combines information from red, green, and blue. Yeah.
How do you calculate how big the first fully connected layer is from that subsample to the fully connected?
How do you calculate it? Oh, that's a good question, actually. So what would happen here? I can't see. Does that say 120? Yeah, so there's 120 nodes here. And every node here is connected to all of these. So in this layer, yeah, I should have made a slide about this. So this is 16. There are 16 of these, and each one is 5 by 5. So the total number of nodes here is 16 times 5 times 5, which is 16 times 16 times 5 times 5 is 1,000, isn't it? It's so there's 1,000 nodes here, and each one of them is connected to these 120 nodes here. So the number of parameters here is enormous. Yeah, there's a bit of a concern here potentially. That's 1,000 nodes and 100. So in this layer alone, there'd be 120,000 weights, and all of them are independent. Yeah. So there's 120,000 parameters in this layer here. And then from here to here, there's not quite so many. It's 120 times 84. Yeah. Okay. Yeah. Yes, I mean, I suppose well, you mean about the number of free parameters? Well, yes. So I guess in this particular case, okay, so in this particular case, there is a pretty big disparity. Yeah, there's 120,000 parameters here and only 500 here. But we'll have a look at some other examples where it's not. Yeah, so that can happen. That there's that there's only a small number in the first layer, but we'll see some examples of bigger networks where the discrepancy isn't quite as big as that. Yeah, yeah.
So the 6 filters in the first layer, why should each of those filters represent a different feature when they're all trained on the same inputs and give us similar?
Well, the same way if you had a 2-layer network with 6 hidden nodes, they would differentiate. Each filter, the backpropagation, naturally, if one filter is already serving a certain purpose, then another filter will automatically try to do something different. Yeah. Yeah.
So the pooling layer will never change the number of feature maps, right? Only the convolution layers will change the number of feature maps.
That's right. Yeah, exactly. Yeah. Good. Okay, I think we'll take a 10-minute break now, and then we'll talk about padding and stride. Yeah.
I've got a question about the exercises.
Yeah, yeah. Good. Okay, so a few more variants of this. So the example that we looked at before, the size of the array shrank as we moved from one layer to the next. So if the input was 32 by 32, then the next layer was only 28 by 28. Now, sometimes we do what's called zero pad. So sometimes we actually want the size of the layer to be preserved, the size of the array to be preserved from one layer to the next. And we achieve that by what's called zero padding. So with zero padding, we allow the filter to run off the edge of the input, and usually the things out here are just treated as having a value of 0. Right, so that weight gets multiplied by 0. These weights don't actually contribute, only the bit that's actually on the image contributes, but this produces a neuron in the next layer. And if we continue this process, you can see that the original layer is 7 by 6, and the next one is also 6 by 7, and the next one is also 6 by 7. So the size of the image is preserved, and you'll see this in TensorFlow. I think if it says padding equals same, that means that it'll have the same size. Effectively, that's zero padding to keep the size of the array the same. Okay. Now, so we were looking at LeNet. Now, this was one of the first. Now we're going to look at a network called AlexNet. So I think this was devised by Alex Krasinski in 2012. This was one of the first kind of industrial scale convolutional networks for image processing, and it was trained on this larger task that I mentioned that had 1 million images and in 1,000 different categories. And this is a sort of picture of this architecture. So it's the same principles, but the numbers have just been scaled up. So we have 5 convolutional layers and then 3 fully connected layers. And there's max pooling. And at the end, there's softmax, but remember, it's softmax with 1,000 categories instead of 10. And because of the the computation that was available at the time, he split the computation up onto 2 different GPUs. And so if you look at this, there's a few kind of weird details here, but he actually had 1 GPU computing the layers here, and another GPU computing these layers up here, and they were largely independent, but there were a few kind of crossover connections between the two. So this was kind of highly engineered to try to make the best possible use of the hardware available at the time. So this made use of so one of the modifications that it made use of that wasn't in the original LeNet is the concept of stride. So the way stride works is this: we compute as before. We put the filter, and we compute this node. But then instead of just sliding it over by 1 pixel, we slide the filter over by, in this case, 2 pixels. So we can specify a stride length s, and in this case, s equals 2. So here, every time we slide the thing over by 2 pixels, and what happens is that the next layer becomes smaller than the original. It shrinks by a factor of s approximately compared to the original image or the previous layer. Right? So here the original image again is 6 by 7, but the array of neurons that we get in the next layer is only 3 by 4. So this is another way of shrinking the array as we move through the network. And this AlexNet actually used a stride of 2. Now, if we try to ask ourselves, well, what's the size of the next layer? Well, it's actually given by this formula here. And when I write this division, this is interpreted as integer division. We throw away the remainder. So let's just have a look at this. Let's just look at 2 separate examples. So first let's look at the example that's shown here. So the J minus M, J is the width of the original image, which in this case is, excuse me, is 9. And M is the size of the filter, which is 3. So J minus M is 9. J minus M is 9 minus 3, so it's the size of this small rectangle here. And in this case, this is 6. This value is 6. 9 minus 3 is 6, and 6 is an exact multiple of the stride length S. So 6 divided by 2 is 3, and we get 3 columns of blue, 3 blue columns in that portion there. But we also get this extra one here because it's the corner of the filter. So this is a kind of, this illustrates the case where this division is an exact number and there's no remainder, right? Now, if we imagined that this is, let's imagine this is slightly smaller. Let's imagine that instead of 9, we only had 8 columns to begin with. This green square would be here, and J minus M would be 5, right? Now, 5 divided by 2 is not, divided by 2 is 2 because we throw away the remainder. But then we add back 1, so we get 3. So you can check that this formula actually gives the right answer in both of those cases, and that kind of shows you the boundary cases. So where there is a remainder and where there isn't a remainder. And this formula actually is a general formula. And finally, stride can be combined with 0 padding. So this is the full generality. So here we've got a stride of 2 and we've got 0 padding. And the formula we get for the size of the next layer is this, that we have to add twice the padding. We've put padding of P on one side and P on the other side. So the white rectangle is J plus 2P minus M. No, sorry, the white rectangle is J plus 2P. We subtract M to get the size of this rectangle here, and then the same logic applies. We divide by S, throw away the remainder if there is one, and add back 1, and that'll tell us the size of this blue array. Okay, so let's look at a... So this is an example taken from a real serious convolutional network from 2012. This is the first convolutional layer of AlexNet. The size of the images here was 224 by 224. We have padding of 2 units at either side. The filters are of size 11. And the stride here is 4, right? So what's the width of the next layer? Well, we just use that formula. So J plus 2P minus M, that's 224 plus 2 times 2 minus 11, and we divide that by 4 and add 1, and we get 55, right? So those neurons in the first layer are going to be in little arrays of size 55 by 55. And then we ask the same questions we asked before. How many weights are there per neuron? So the filters are 11 by 11, and it's a color image. So it would be for each 11 by 11 by 3 plus the bias. Yeah, so that turns out to be 364. Now, how many neurons are there? How many neurons are there in the first layer? Somebody tell me. Right, exactly. 55 times 55 times 96, right? So someone was asking why we need 6 layers. This guy had 96. Yeah, it seems a bit excessive, but that's what he had. Yeah. So that's 290,400. How many connections? Well, we multiply those two numbers together, which turns out to be this. 105 million. And this is just in the first layer, remember. And how many independent parameters? Well, for each filter, we've got 364. And how many filters are there? 90. So it's 96 times 364. So we're getting pretty serious here. We've got 34,944 free independent parameters just in the first layer. Okay. Now, another, there were a few other innovations that this network introduced that I'll talk about in a minute, but let's start with this one, which is overlapping pooling. Now, this, we'll just try to, this always like fails the first time. I don't know what's going on. Let me try the same trick again. All right. Ah, thank God, yes. It's like a car engine that needs to be gently persuaded somehow. So the type of pooling the type of max pooling that we talked about before was like you'd look at this group of 4 and you pick the maximum, and then you look at that group of 4 and pick the maximum, and you keep going. So if you divide the whole thing into disjoint sets of 4, and in each one you pick out the maximum, right? So each number only could contribute to at most 1 neuron in the next layer. Now, what these guys did with AlexNet, they had a pool. They did max pooling, but with 3 by 3. A pooling size of 3 by 3, but they had a stride of only 2. So they'd pick the largest of these numbers, and the largest of these numbers, and the largest of these numbers, and sort of went in that fashion. Now, while we're here, someone was asking at the break, why does max pooling work? Yeah, so max pooling is a bit controversial. I think Jeff Hinton has been quoted as saying that he's not happy with it. But somehow it does seem to work reasonably well for these image processing tasks. And I guess if you try to ask why it works, I think the answer would be, remember that these these hidden nodes in the network are trying to extract certain features. Yeah, they might, let's imagine there's a node that's trying to figure out whether it can find a feather in that part of the image. And so the pooling has the effect of like trying to tell whether there's a feather either at this location or at some nearby location. It's sort of looking at 4 nearby areas that overlap and trying to look for a particular feature, whether a feature occurs in any of those 4 nearby positions. You can think of it that way. You know, is there a feather here, 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 or here? And you know, if there is, that sort of moves up to the next layer. You know, so you can kind of understand why that may be beneficial for these image processing. But this overlapping pooling. So you see this when we have the pooling size different from the stride, you get this slightly unusual effect that the thing overlaps. So you see what's the biggest number here, and what's the biggest number here, and what's the biggest number here, and what's the biggest number here. So there's something a little bit odd about this in my view, because the same 9 is the same high value could get copied to 4 neurons in the next layer. Yeah. So it seems a little bit unusual, but apparently in this particular context it somehow gave good results. And these are sort of just parameters that people fiddle with you know, to see how, you know, it sort of may depend on what other things are going on with your architecture. So it was max pooling with width 3 and stride 2. So then you can ask, what's the size of the next layer? Well, again, it's the same sort of arithmetic that goes on here. If j is the size of the previous layer, you have to subtract the filter size and then divide by the stride and add 1, right? So if your first hidden layer has networks in a 55 by 55 array, and you do this max pooling, you would end up with something that's 27 by 27. And then this is sort of a slightly trick question that picks up on what someone else was asking about this during the break. How many independent parameters do the pooling layers add, or they actually don't add any? Because there's no weight here to be trained. All it's doing is looking at a bunch of numbers and picking out the maximum. Yeah. Okay, and that's the filters I showed you already. Okay, so that's convolution networks. Now, does anyone have any questions about this? Yes?
Would it be possible if pooling would reduce the number of if you did it in a specific
Could pooling reduce the number of independent parameters? Indirectly, it kind of does, because it reduces the number of neurons in the next layer, and therefore you're going to have fewer parameters from that layer to the layer beyond it. Yeah.
You're taking into account essentially less inputs.
That's right. Yeah.
So you're almost throwing away some. If you throw away too much, you lose.
You are throwing away. Yes, I think that's Jeff Hinton's objection to this. You are. It certainly looks as if you're throwing away information. Yeah, which seems rather weird. Yeah. Okay, the question was if people have tried taking the average or using a Gaussian or something. Well, I'm not sure about that, but it is possible to build a network without any pooling at all and still reduce the size of the layers. So if you do this stride thing, so there's this kind of architecture that's called an all convolutional network that doesn't have any pooling. So if you do that, you see what happened here, without any pooling, just because of the stride, the size went down by a factor of 2 effective. I've basically halved the size of the layer from one. I've halved the size of the array from one layer to the next. So if I did this kind of thing multiple times, then I could get the same effect without having any max pooling, without having any pooling. Yeah, and personally, I kind of like the all-convolutional network. It seems like you're not throwing away information. You're kind of, it's cleaner somehow, yeah. Yeah? Could you use another function for the pooling? Okay, the question is, can you use another function for the pooling? I think you could, theoretically, yeah, you could use the mean or the median. These things go back. There was, in classical image processing, there were these things called the mean filter and the median filter that just didn't have any layers, but just directly modified an image. So these are sort of deep equivalents of that. But people probably have tried these things, but I don't know too much about the details. Yeah, it's a good question. Yeah. Okay. Other applications of convolutional networks that's not image processing. Well, okay, first of all, games that are on a 2x2 grid, chess and Go. So the AlphaZero makes use of this. That's one application. Now, another thing is, so I talked about time, right? So if you've got, say, audio processing, speech processing, let's say, or some sound signal, it's only in one dimension, but I can actually do convolution. There is a way to use a convolutional network in one dimension, and there's been some recent discussion about this. There was a paper that came out a few months ago that was claiming that like a one-dimensional convolutional network might do a better job at time series processing than certain other methods. So that's that's another example. So a one-dimensional example. Yeah. So the question was with max pooling, if the pool went off the edge, well, you'd just take the maximum of whatever numbers are there, I think. Yeah. Overlapping. That's a good question. I think. Okay, so let me get back to this. I think if we believe this formula, then okay. So the question was about max pooling when you get to the edge. If we believe this formula, then it doesn't include any padding. So you would actually you would only include situations where all of the numbers were within the image. Yeah, you wouldn't be allowed to go over the edge. Yeah. Lynette, yeah. This one, yeah.
Yeah. So in the last two layer, what happened there? Why suddenly we change it to a one-dimensional layer there? Like C5 and F6, they are one-dimensional.
Yeah, the one-dimensional layers. So these last two layers are just simply fully connected layers, the same as the old-fashioned neural networks. Every node is connected to every other node. So I guess the idea is that these... these earlier, the convolutional layers extract out sort of localized features, but they gradually become in bigger parts of the network. But then the last layers just combine that information together. So yeah, I mean, you can think about it. If you find a beak and some feathers and an eye and you put them together, then that's probably a bird. Yeah. So it combines the features.
How do you convert that two-dimensional measures to single value, like from S4 to C5?
Yeah. Every node is connected to every node in one layer is connected to every node in the next layer. And then the output layer, the number of nodes in the output layer is equal to the number of different classes. So it's just whichever output, you just look at how big the each output is. Yeah. Okay. Yeah. R120. Well, this is I was just, they just choose that, they've just chosen that number for some reason, but the 1,000 nodes in the previous layer, every one of them is connected to all of these 120 nodes in that layer. So there's like 120,000 weights, parameters just in that from C4 to C5. Yeah, it's just fully connected. So you forget about when moving from here to here, you just treat this as if it's 1,000 numbers. You forget about the fact that it's divided into 16 different filters. You just treat it as if it was flat somehow. Yeah. Yeah.
We have F6 layer, which is 84. For the layer before, why is it C5 instead of F5? And I suppose F stands for full.
Ah, God, that's a very good point. I copied this graph. I copied this graphic from somewhere. I think it should say F5 because that's fully connected as well. Yeah, yeah. Not C5. Yeah. Yeah. Well, usually the stride is just in a regular pattern, but this feeds into data augmentation. Yeah, sometimes I'll talk about data augmentation in a minute. Yeah. Okay, so let's just in the time we got left, I'm just going to talk a little bit more about this AlexNet and some of the other details of what was done there. Okay, so I mentioned the MNIST data set, CIFAR. So this is the image net. So as I said, it's 1,000 classes and approximately 1 million, actually a little bit more, 1.2 million images. So there's approximately 1,000 images of in each class. It varies a little bit from class to class. And these 1,000 classes include things like elephants, irises, what is that? That's violets, I think. Elephants, ships, pumpkins, jack-o'-lanterns, dogs. So there's quite a few quite detailed classes. And this, well, I was just going to mention, we'll talk about this next week, but sometimes we try to do something more sophisticated than just image classification. We try to do segmentation. So the task we've been talking about so far, you just want to identify the main object in an image. But sometimes, of course, an image has multiple objects in it. So that sort of would add extra complexity. Okay, so this is the LINET that we looked at in great detail. Right, so this is a little bit of a history of this ImageNet competition and the different architectures that won it in different years. So the winner in 2012 was this AlexNet, which had 8 layers. And then in 2014, there was a network called VGG, which had 19 layers. And then there was GoogleNet. And then 2015 was ResNet. And I think, I'm not sure if I think 2016 was a DenseNet. So we'll get to the DenseNet, we'll get to the ResNets and the DenseNets. But if you just look at the top 3, the principles are basically the same, but it just varies in terms of how many convolutional layers and the size of the number of filters and the size of the filters and those sort of details. Okay, so this is the AlexNet we discussed. Now, if you count the number of neurons and the number of parameters, we did it for the first layer and we came up with 130,000. But if you actually go through the entire network and it turns out the whole network has 650,000 neurons, 630 million connections, 60 million free parameters. Now, for those of you who know, if you took the machine learning course or you know anything about or you're familiar with machine learning, this looks kind of strange, or you can tell that there's a danger of overfitting here, right? Because you've got more free parameters than you have data, right? How much data do you have? Well, depends how you measure it, but if you measure it in terms of the number of images, because each image is telling you one classification, right? So each image is, in a sense, only one. You've got a million images, but you've got 60 million free parameters that suggests that there's a danger of overfitting. Now, and so there's a little bit of a sort of mystery still surrounding these deep convolutional networks that you would expect them to, in some sense, you would expect them to overfit more than they do. But there are some tricks that people have tried to use to reduce the overfitting, at least to some extent. Okay. So some of these, okay, so we talked about this. So it's rectified linear units, overlapping pooling, stochastic gradient descent with momentum and weight decay. So we talked about the momentum and the weight decay. That wasn't just abstract ideas. Those things are actually used in practice, right? So if you can look in the paper what the parameters were, but they had weight decay and momentum. Now, these two things here I'll talk about. These are to reduce the overfitting. So one of them is data augmentation and the other one is dropout. So let's first talk about data augmentation. So data augmentation is saying, well, I've only got 1 million images to train on, but is there a way that I can create new images from those images? Can I can I expand my data set by creating new images that are similar to the ones I've been given? Right? Yeah, exactly. So there's multiple ways to do this. So the first thing is to do with cropping. So, sorry, what were you going to say? Tilt, yeah. And reflecting, yeah. So reflecting is good. So I'm given an image. Maybe that. How can we? I don't know how we can visually well, let's just look at these images to start with. So if I take an image of an elephant and I reflect it, flip it left to right. If I turn it upside down, it's going to look unusual, right? It'll look like the elephant standing on his head. But if I flip it left to right, it's going to look pretty natural, right? In fact, sometimes you see this on YouTube. Right? Like people would reflect something left to right to make it less likely that it'll be detected that they've that they've copied it from some TV show, right? So so that effectively kind of doubles the number of images. And think about the architecture of the network. If you reflect the image, you're really training on something new, right? So that doubles the number of images already. Now, what else can you do? You were suggesting to tilt it a little bit. I think you could do that. I don't know if it's common to do that, but you could tilt it a little bit. If you tilt it too much, it's going to look strange. But if you tilt these images a little bit, they would still look natural, right? The other thing we can do is crop the image, or just shift it a little bit by 1 pixel in different directions, or crop it. So if the original images are 227, well, this is what they did with the AlexNet. The original images are 227 by 227, but they crop it to make a smaller image. They chop off a few pixels at the side to make a smaller image that's 224 by 224. So they chop off 3 rows and 3 columns, but it's not, it could be 3 rows from the top, or 2 rows from the top and 1 from the bottom, or 1 and 2, or 0 and 3. So there's 4 choices for which rows to chop off, and 4 choices for which columns to chop off. And again, it kind of ties into the network architecture. Remember, the network had a stride of 4. The first hidden layer had a stride of 4. So the stride of 4, if you crop the image in different ways, those filters are actually seeing different parts of the image, right? Because of the stride of 4. So there's something kind of a bit clever about this, yeah. So this is what they did, right? So they by cropping in different ways, I can make many different images from the original image, and I can train on them separately. I can horizontally reflect. And then what about the crop? So you think, okay, so the cropping, so again, there's little details here. So because I'm cropping, my network now is expecting an image of size 224 instead of 227. So what do I do when I'm actually testing an image? Well, I'll crop the tested image in 10 different ways as well. And then I'll feed all 10 of them into the network. I'll get 10 different predictions, and then I'll average them out. So this is just a kind of little tricks for improving the accuracy. And there are other things I can do to the image. I can make slight changes to the intensity of the red, green, and blue channels. So I don't know if any of you have played with Photoshop or GIMP. You take an image and then it may look, the colors may look a bit washed out because of the bright sunlight or something, and you can play with it and make it look a bit more colorful. But what you'll notice is that when we look at it, it still kind of looks like, we still recognize it as the same object. Yeah, so they do that as well. Yeah, so there's different kinds of data augmentation. And the other thing that they do is is dropout. Okay, so dropout. This was actually on the slides from an earlier thing, but we didn't talk about it yet. Yeah.
For the data augmentation, especially recreating images, are we doing that manually or automatically?
Data augmentation. Are you doing it manually or automatically? So are you talking about in TensorFlow or are you talking about? Yeah, it could be done either way potentially. So you could start with you could have your million images stored somewhere, and then you could from each of those you could create 10 more. Or it can be done on the fly. So every time you create a mini batch for training, you could generate new versions of the image. So I think just looking at the way it's done in TensorFlow, I think both options are available. It's possible to just do it like on the fly when you create a training batch.
If we were doing that automatically, there's a chance that the recreated image can be quite ridiculous.
So the question was, could the recreated image be ridiculous? You mean because of cropping or because of tilting or?
Or maybe reflection.
Okay, so the cropping, if you're only cropping, if it's 227 by 227 and you're only cropping off 3 rows and columns, it's hard. I doubt it would change the image that much. I doubt the image would become ridiculous. The red, green, and blue, it might look a little bit funny. Yeah, if you're trying to tilt it, well, but you were talking about, the reflection. Yeah, I mean, sometimes I've watched, most of us have probably had this experience that you watch a scene from a TV show on YouTube and then sometimes you get through the entire scene and then you find out later that it was, and you didn't even notice, and you find out later that it was reflected. I mean, who's had that experience? I've certainly had it. So I think it's probably unusual. It's only if there's you only sort of notice if there's a clock in the. Well, sometimes you just know, I've seen this set before and I know that the door was supposed to be on the right-hand side, but that's just from your background knowledge. If there's a clock there, then sometimes you notice that the clock is the wrong way around, or that people are writing with their left hand, that a lot of people are writing with their left hand. I don't know, there's only little subtle things like that. Or people are driving on the wrong side of the road. I don't know. Reflecting is pretty safe most of the time, I think. Yeah?
So what's the purpose of data augmentation? Is it for training?
It's to make the network more robust. Yeah, you're increasing the size of the training set. So it's to improve the generalization. The aim of it is to improve generalization. Yeah, so the way you would test whether the data augmentation is doing a good job is you'd have a training set and a test set and see whether the accuracy improves on the test set.
So actually we are cropping same image and if we are training again, but it's almost like same image but cropped. Is it efficient or?
The question is whether it's efficient. Yeah, so when you train the neural network, even though there's a million images, you're actually... perhaps I should have mentioned this. These competition winners, like that AlexNet, with the hardware of the time, it was trained for 2 days. Like they got the biggest GPUs that were available and they trained it continuously for 2 days. And so even though there's a million images, it would be seeing each image many, many times. So it's beneficial if it's presented in slightly differently each time. Yeah. So yeah.
You mentioned altering like RGB values.
Yeah.
Say if you knew that the data you were working with was noisy to begin with.
Yeah.
Would it also be valid to like introduce some Gaussian noise into the image?
That's another thing that's sometimes done is introducing Gaussian noise. I don't know if it's off. It's not usually done, I think, for this kind of task, but when we get later in the course to image generation, or sometimes like denoise, like sometimes if it's image generation or auto encoding, they often do inject that kind of noise. They just pick a pixel and add some random value to it. Yeah. Sorry, was there something else about your question, or? Yeah. No. Oh, yeah.
So can you use different color space for that image augmentation, like the HSV or YCR?
Oh, okay. The question was can you use HSV instead of RGB in this context? So in the context of image generation, that would make probably a difference. If the input is an image, it probably doesn't make much difference whether it's HSV or RGB because it's a linear combination. So you could transform one into the other. Yeah. If the output is an image, then it's kind of a different story. Yeah. Yeah. Time series. Yeah. Okay, you're asking about convolution for time series. Look, it's, to be honest, it's getting a little bit out. I'd have to go away. I'll take your question on notice and see if I can find out more about it. But I think normally the straightforward way is just to convolve in one direction and not in two directions. Yeah, so, and then you may convolve at like at different scales, kind of thing. So you may have like a filter that's with a very small range, and then another filter with a big range, and you may sort of combine them together. Yeah. Good. There's one more thing about this, Alex, and I don't quite understand the details of this, but I think the colors were, you're asking about HSV versus, I think, yeah, I told you there were these two separate GPUs that process different parts of the network. I think that the colors were handled slightly differently somehow in those two networks. But I don't know exactly. So one of the lower GPU, for some reason, the lower GPU tended to learn more color-specific filters. Yeah. Yeah. So the input was handled a little bit differently, but yeah, I'm not sure exactly the details. Sorry, I got to. So just going back to this geometry, yeah. Okay, let's just remind ourselves. Yeah, so I kept talking about rectified linear units, so that's what that activation function looks like. And then Yeah, so this dropout. Yeah. So this is a technique that works for any kind of deep neural network, but has also proven useful for these convolutional networks. So, and this will probably be the last topic for today. So, the way this works is as follows: we have a network, and we have a mini batch or a set of images. Let's think about this in relation to image processing. So you've got a set of images, and we randomly select some fraction of the nodes in the network which are not going to be active, not going to be used for this particular set of images, right? So I have, the training set is divided into little mini batches that might be generated on the fly. So I might have a set of 150 images that I'm training on at the moment. So I choose certain nodes are not going to be used for this particular set of images. And then when I move on to the next set of images, I choose some other set of nodes randomly. And normally it's 50%. Normally I choose half of the nodes, and they're not going to be used, right? So only the nodes that are crossed out are not used for this particular part of the training. Only the nodes that remain are being used. And the way this is implemented is that the ones that are crossed out, you just multiply their activation by 0, basically, or you don't compute it at all. And so after you've sort of removed that, and in some cases the inputs, sometimes even some of the inputs may be ignored, but sometimes it's just the hidden nodes. And it happens at every layer. And I train the network. So the remaining nodes have to try to do the whole job, basically. And I choose a different subset of nodes for each mini batch. Now, what this does is it effectively it encourages redundancy in the network. Yeah, it's sort of, maybe the part of the inspiration for this was from the human brain. There are certain nodes, some neurons, sometimes they fire, sometimes they don't fire, but when they're not firing, other neurons kind of take over their role or something like this. So if you train the network with dropout, the network is never relying heavily on one particular neuron. So if certain neurons are removed, it has to be able to function with the remaining neurons. So that's what happens during the training. Now, what happens during the testing? Well, you see, if you always trained like this, but then you tested it with the full network, potentially there could be a problem, because during the training, like this node is connected to all nodes in the previous layer, but during the training, it's used to receiving input only from half of the nodes. It doesn't know which half, but whenever it's trained, it's only receiving input from some random subset of the previous nodes in the previous layer, half of them. And so if it suddenly receives input from all the nodes in the previous layer, it would be getting twice as much activation to what it's used to, and then it wouldn't compute properly, right? But there's a very nice trick to get around this, which is that after you finish training, when you're deploying the network, you do use all the use all the nodes, but the activation of each node is multiplied by the same percentage as the dropout. So if 50% of the nodes get dropped out, then when you're testing, you multiply the activation of each node by 50%. If only 20% of the nodes were dropped out, then at the end you'd multiply every activation by 80%, because that's the fraction of nodes that aren't dropped out. And so if you think about it, this node, it's used to receiving inputs from, let's say, only these two nodes. Now it's receiving from everyone, but they're all multiplied by a half. So on average, it's getting the same activation that it would have got in training. I don't know if that's clear, but that is actually the case. Yeah, so it's on average, each node is receiving the same input that it's receiving actually an average of what it would receive if half the nodes from the previous layer were removed. Because it's receiving from all of them, but only at 50% of the value from each one. Does that make sense? Yeah. So this actually works also to improve the generalization of the network. Yeah?
Why don't we just use a smaller number of nodes if we were to drop them out anyway?
So the question is, if we were going to drop them out, why don't we just use a smaller number of nodes? Well, the answer is somehow this gives better results. But let me try to explain to you why this gives better generalization. Okay.
Is it to avoid overfitting?
It's to avoid overfitting. That's right. So, okay, so sorry, this just repeats what I was saying. So, when the training is finished, you just multiply the activation by the same fraction. Right, so dropout forces the network to achieve redundancy because it must deal with situations where some features are missing. Now, another way to view dropout is that it implicitly simulates an ensemble of different architectures. Okay, now this is sort of part of machine learning. I try to this is sort of a big topic in itself, but I'll try to summarize it as briefly as I can. So there's this general principle in machine learning that you often get a better answer if you train multiple learners on the same task and then have them vote. You often end up with a more accurate answer than if you just had one learner. And especially if I train different types of learners. So if you look at these like Kaggle competitions, you often find that the winning entries use this kind of approach. They'll pick 3 different neural networks with different numbers of hidden nodes and different architectures. They'll train each one on the task. And then they'll use 4 different types of support vector machines with different representations and slightly different, and they'll train all of those. And then they'll take the 3 neural networks and the 4 support vector machines, and somehow all 7 of these will vote on a class, and whatever the majority vote on, that's the one you're going to pick, right? So because you're combining information from different kinds of learner, you get a better answer somehow, right? So it's kind of a trick, but this is what's often done. Now, this is, okay, look, I won't, bagging is another approach. Like, let's say you don't want to use different architectures, you just want the same architecture. Sometimes we choose different training sets, so I have 100 training items. This is another trick that sometimes used. It's called bagging. I have 100 training items. I train a neural network on those 100 training items. well, if I train the same neural network on those 100 training items with different initial weights, I might get a slightly different answer, but probably not much different, right? So the trick people use is they say, well, I've got 100 items here. I'm going to randomly pick 100 items from these 100 items, but with replacement. So I pick one, and I make a note of it, but I put it back in the bag. And then I pick another one, and I make a note of that, but I put it back in the bag. So if I pick 100, some things will get picked twice, or 3 times even, but some things won't get picked at all. But I've got a new set of 100 items, and I can train on those 100 items. And there's a lot of sort of mathematical theory behind this, but you know, I can repeat this process 10 times. So I've got neural networks with the same architecture, but each one's been trained on a slightly different training set, and then I can ensemble them together, and it turns out that actually gives a better result than just one classifier, right? So the other way to think about dropout is that it's kind of an implicit ensemble method. So if you so let's just think about this theoretically. If I could from my original network, I could make 100 different networks by randomly removing 50% of the nodes, and then starting from the same network and randomly removing a different 50% of the nodes. You know, I could create 100 networks. I could train each network on the full set of data, and then they could all vote. Now, it would be very expensive to do that. You know, if it takes 2 days to train each one of them, it's going to take 100, and I want to train 100, then it's going to take 200 days, right? So it's very, very expensive. But dropout kind of, in principle, achieves the same thing, but does it much more efficiently, right? So there's like mathematical arguments behind this, that if I do this dropout procedure, and then in the end I just use the whole architecture. In some sense, it's kind of equivalent in a way to ensembling over these different subnetworks. Yeah. So it's a kind of implicit ensembling. All right. I think that's yes.
Can we have a neural network without the bias value? The other weights can compensate the value of the bias?
Okay, the question was, can you have a neural network without the bias? Yes, you can. And with supervised learning, it doesn't make much of a difference. But with reinforcement learning on video games and stuff, sometimes it works better if you don't have bias in some of the layers. Yeah. Okay. So if you, I'll be here if you want to ask any more questions, and otherwise I'll see you next week.
The dropout function will kind of, when you train half of the data set, you switch it to those one not being activated and switch this into the non-activated, and then train it again another half.
You swap the...
Yeah.
You swap
but I don't know my memory is right or not.
haven't
So-
heard of that, but
so-
it could be done.
Yeah, it's swap that, so it divide by 2, it times the percentage of the dropout rate. So it times, for example, it trains